Hello, this video is a demonstration of a project in which a chessbot was implemented using a Minimax search algorithm. Let's start with explaining how the chess player works. When it's the AI's turn, it will um, it will choose a move to make. The first few moves in the game are pre-generated by handmade openings. Um, I developed uh, two moves of some common openings, such as Caro-Kann defense or the Queen's Gambit. The black player generates a response to the opening if it has discovered that's one in the playbook. After the program escapes the opening, the Minimax algorithm is used to find the best move to make. So at the beginning, the best move values as well as the alpha beta values are set to the opposite of the optimum value. For example, negative infinity for white. The algorithm then gathers every single piece on the board and the moves that it's able to make and generates a new board state from those pieces. During the board state generation, we make a hard copy of the current board and also perform a check for pawn promotions. Each of these board states generates a new recursion of the Minimax search function. The Minimax search will take the current status of the game. If it's not at max depth, it will generate the possible outcomes again by generating more recursions. However, if it reaches the max depth or the game is in a checkmate state, the Minimax search will return a heuristic, which is a score of how well this position is. The best move, or the score of it, that's achieved by a particular player is saved into the alpha beta values. These values are used for pruning the tree and reducing the time required for the search. The Minimax search continues until the board states are explored or pruned, until it finds a move with the best value. The Minimax algorithm assumes that both players play in the most optimal way to decide which of the values is optimal. Let's now peek at the heuristic function that governs what type of behavior is considered optimal. So the heuristic function goes through every square of the board, collecting the pieces. To generate a heuristic for each piece, we evaluate its position and how beneficial it is. First, I use piece square tables to apply a pre-generated score bonus or penalty for a particular piece to stay on a particular square. I then build an attack table. So first I go through pawns and form the attack table for them. And then I collect all the possible moves that a piece can make. And if the move is an attack move, then I also update the attack table there. So then we iterate the pieces of each player and we apply a multiplier depending on how safe or how threatened a piece is, determined by the attack tables. the value is also determined by the type of the piece, such as queens are worth significantly more than pawns. Up next, let's watch some gameplay and see how the bot performs. So the bot plays quite aggressively, um, focusing much more on threatening my pieces than keeping a good structure or protecting its pieces. This causes the bot to often make mistakes where it loses a strong piece due to a miscalculation of the threat value. It's mostly due to the fact that the threat values were chosen arbitrarily and were quite difficult to balance to achieve the right behavior. In this game, I actually lose against the bot, as I've made some mistakes that the bot has easily exploited. Thanks to the minimax search, the bot can see some very efficient trades that are sometimes not visible from the first point of view. The bot could possibly be improved by upgrading its structure definition so that it puts more focus on protecting its own units. Perhaps adding a heuristic for occupying space will keep the units behind the pawn structure. In this match, I made less mistakes and was actually able to beat the bot. Or stalemated because I made a small mistake at the end. Next up, we will watch bot versus bot matches. So here we can see the bot making some threatening attacks, which leads to quickly losing the queen by the white player. Or both players, in fact. The bot made a decision to castle in that position. And the game continues with a large number of pieces being lost by both players, due to the fact they prioritize attack. In this scenario, the bot got stuck in a loop when reaching the end game, unable to finish the game. This is probably due to not enough material, as achieving a checkmate with just a bishop is quite difficult. In this next game, the bot will achieve a checkmate state successfully. As you can see, the bot makes some logical and efficient trades and then quickly reaches a checkmate. As you can see, every game has a different opening, giving some variety into the bot games. The developed program successfully plays a game of chess at an intermediate level, meeting the research objective. It can find the optimal move in a reasonable time of under 15 seconds. It does sometimes make mistakes where it loses a valuable piece, but it plays reasonably well.